Huge thanks to Jacob for getting us caught up on time. My name is Brent Griffin. Today I'm going to be talking about learning robot perception and control using vision with action. And when I accepted this talk, I was the perception lead at Agility Robotics. You can see our robot Digit working in a GXO facility in Atlanta on the top right. You can also see Digit holding the Best New Innovation Award at ProMat in the middle right. But a lot of the work that I did there is confidential. So I'll be speaking primarily about work that I did when I was at U of M as a research scientist. I'm also excited to say that I will be joining Voxel 51 next week as a research scientist. So it's an honor to be a part of this seminar series. Really enjoyed the previous talks. And yeah, just really appreciate Jacob getting us back on track. So let's keep this rolling. So I'm going to start out with a quote, and that's: vision with action is merely a dream. Action without vision just passes the time. Vision with action can change the world. And I think this quote is a good description of the relationship between computer vision and robotics as it stands today. Computer vision has seen rampant advances in terms of using deep learning with a massive amount of data. On the other hand, robotics as it's deployed today is primarily to highly structured environments like warehouses because, in my opinion, robots are not yet sufficiently taking advantage of the massive amount of data that they generate so that they could learn to operate and continue to improve their own vision systems in, let's say, unstructured environments. And so if we can couple computer vision with robot actions, make use of that massive amount of data that robots continue to generate, and have it so that robots can improve their own vision systems and resolve uncertainty in new environments and things that change, I think this will be the introduction of a technology that can truly change the world. So with that, I'm going to be talking about just a couple topics today. One is going to be how we use deep learning with classic visual servo control to do mobile manipulation. Jason showed a video of this a little bit earlier today. I'm also going to be presenting some work on what we call robot-supervised learning and domain adaptation. And this is how we can use robotics to generate new annotation and training data that the robot can use to improve its own vision system. And then finally, I'm going to talk about how we can learn to estimate depth from video with action. And this is both for an entire image and individual objects that we're able to detect or segment. So the initial motivation for this initial work was working with Jason at U of M. We were awarded a project with TRI, and they additionally provided a human support robot, or HSR. And the primary motivation of Toyota developing this robot is to help care for disabled individuals in Japan's aging population. But at the time that they gave this robot to us, HSR was unable to find or manipulate objects in unstructured environments. And so as you can see in this demo that they had before we got the robot, they're putting fiducial markers on things like the water bottle and the wheelchair, so HSR can understand where these task relevant objects are. And so we agreed to help Toyota address this limitation and also participate in the HSR University Challenge. Now, a little bit about the HSR University Challenge. This was the same organizers from the DARPA Robotics Challenge back in 2015. And it really required teams from each of these universities to operate outside of their own area of specialization and integrate many technical components together to be able to perform end-to-end real-world tasks. And the schools that participated include schools like Stanford, University of Michigan, MIT, Berkeley, among all the schools shown below. So this was a very competitive competition that TRI was hosting. And although it started with a fairly initial task, as I'll show, these gradually got much, much harder. So the first task, you had a single 5-minute trial. You would log in via a live web meeting, and you would basically pour 3 blocks onto a tray, and then HSR would have to place each one of those blocks onto a specific shelf or cubby based on the color of that block. So when we first started working on this, we figured, okay, they're basic blocks. Let's just use the RGBD camera that's mounted on HSR's head. We'll just classify objects in the RGB image based on their color and segmentation, and then we can figure out the 3D geometry using depth after the fact. And so when we would do grass planning based on this paradigm, one thing that we found is because HSR has a very low degree of freedom arm, it actually has to move its base to perform any kind of a grasp. And because the base motion, especially in translation, would introduce errors, we would often miss grasps. And so this wasn't really that reliable. In addition to other problems with using the depth camera, you might be missing some of the pixels for the tray or red blocks. And also, it's unlikely that this kind of a simple approach would really scale to real-world objects that are more complicated than these colored blocks. So we were testing plan B, which was just using RGB-based grasping. And part of the motivation for this is that HSR had an end effector camera right alongside of its gripper. And so if we could locate objects using this camera, then we would be directly tied to the frame that we're going to be grasping from. And we could similarly use this as a way to grasp objects. So you can see an example image of what it looks like from the grasp camera when HSR is looking down at the tray with the blocks. Now, one thing we use as a starting point, which is classic visual servo control, which broadly speaking is using visual data as input to a servo feedback control loop. I had background in control, so I was very comfortable with this. And first part of feedback control is you need an error. And this is just the difference between some set of image-based features S that you define, as well as their desired position S star. Now, if we looked at the existing literature, there are essentially decades of fiducial markers in structured settings, so not that much different than the work that Toyota had already been doing. On the other hand, Jason and I had previously collaborated on some work where we'd applied deep learning to video object segmentation. And what we found is that we could use these algorithms to very reliably segment objects in video, even if the object was dynamic and changing, if the camera was moving, or both. And so what we did is we just repurposed this technology so that we could use this as a way to get visual feedback on ordinary objects in unstructured setting. And this is what gave us our visual servo control error. Now, from there, we actually need to control the robot. And so we need to relate our control inputs delta Q to reduce errors using what's called a pseudo inverse feature Jacobian. Now, the details here aren't that important, but the reason why I bring it up is because we had to develop our own approach to learn this control in real time using what we call a hard-mode and update. So I'm going to show you an example of this on the next slide. Here we have HSR. It's starting with the segment the object in view. It's initializing control policy, and within 14 time steps, it's able to learn a control policy such that it can center and locate on the object that it's interested in. Now, to contrast this with previous work, if we try to use off-the-shelf methods, the robot would basically crash into the wall before it had learned a policy that it could use. So from here, we're able to locate objects, but then we can additionally use segmentation for grasping. And if you think about a segmentation of an object for the gripper camera, the segmentation mask itself essentially represents a projection of that object into the image plane. And so we did the same thing for the graspable space of the gripper relative to the camera. And then we would just rotate that block of graspable space so that we could minimize the IOU with the segmentation mask of the object. The reason why we would do this is because we were doing an antipodal grasp where we grasp from 2 points on each side of the object. And if we were trying to grasp on the long axis, it could potentially stall the gripper from closing. But if we grasp the short axis, then we're most likely to have a successful grasp. And we found that this worked for the majority of the YCB dataset objects, which is pretty standard in robot manipulation. So when it came to the first HSR challenge, we knew that we could complete all of the tasks from the practice that we'd done. What we didn't know is that a time of 2 minutes and 50 seconds would be fast enough to kind of beat out the competition. But we were kind of surprised, I guess, in terms of how hard it was to put together a full solution from the other teams. And so to give you an example of this, about a week before we went into the first challenge, we got an email from TRI saying, we're going to change the setup of the challenge because it's impossible to place objects behind the tray on the shelf. And we'd actually done this in practice, and you have to make smart use of the range of the end effector when it's fully extended and the motion of the base and how it's omnidirectional. But clearly, as you can see from the video here, it's possible. So advocated that, can we please just do the challenge in its original form, to do this and complete the task. Now, the team that came in second place was close behind in terms of time. They were able to complete the task in 3 minutes and 30 seconds. They're using the head camera, the RGB-D camera. And I think with the tray on the side, the reason why they could get away with this is because they do almost pure rotation with the base and no translation. And so this removes some of that error of the base motion that I was referencing to earlier. But yeah, it took more time to do the full RGB-D base planning versus visual servoing. And you did need the tray to be at the side of the robot with almost no motion of the base. And then the third place team used no tray, had Vicon reflectors on every object, and they were only able to grasp one of the 3 objects. And the remaining teams completed 0 grasps. So the point of this is that this was actually much harder than the organizers of this challenge originally thought. And so when we went to the second challenge, they kept most of it the same, but they added a banana peel to try to make a little bit of confusion with the yellow block. because we were using a video object segmentation method, our algorithm telling the difference between a yellow block and a banana peel is actually pretty straightforward. But this was a struggle for the other team. So the second place team mistook the block as a banana, and the third place team similarly mistook a banana as a block on their second try. When we get to the third challenge, we started using a custom Alexa app. They give voice commands to HSR. This could give us guidance to HSR, tell it which tasks to perform first, give it feedback. And we were able to complete all the objects in this, which included like a crumpled up dollar bill and some trash, except for the kitchen tongs, which were located at the near end of the tray. Now, only 2 of the 8 teams attempted the full challenge, and the second place team in this case was only able to place 1 of the 6 objects after multiple attempts. So again, very challenging problem to put all these things together and have them work reliably in that 5-minute time slot. The other thing I'll mention about the way that we learned visual control is that we could do this for different cameras that were available on the robot and using different actuators. So if we look at this example here, I'm going to be moving throughout the room that HSR is in, and it's going to be able to track me using its head camera. And this is using a learned visual serial control policy where instead of using the gripper camera and the base actuation, we're just using the yaw and pitch of the head and the RGBD camera. And after we learn this policy, we can then freeze the weights, have the objects move around, they can be moving, and it's fine. We have a learned control policy for that set of actuators in that camera. And we use this in the 4th challenge where we had to pick up objects that were now not just on the tray, but placed all over the lab. And so you can see HSR here is putting cups in specific bins and other garbage items in a different bin. But we leverage this ability to have HSR track us in part of the challenge. So at this point, HSR... And we had HSR ask us, where is the rag? I don't know where it is. HSR follows me based on a segmentation mask on my clothing. I can show it where the rag is, and then HSR is able to complete the task by using its grass camera to go and grab the object like the other objects in the challenge. In the 5th challenge, they made things challenging again. This was probably the hardest challenge. One was because they had these large deformable objects that you had to go back and regrass to place into the shelf. But the actual hardest part of this challenge was they asked us to pick up a chip bag and place it inside of one of these dino cups. Now, this was hard for all the reasons of the previous challenges, but the other part of it is the precision required to place this chip bag inside of the cup was very high. So our approach was we used video object segmentation to identify both the chip bag and the cup. We picked up the chip bag using the sucker that was on the back of HSR's gripper, but then we had to actually use the anti-bowl to grass to locate the cup, make sure it was precisely located, and then put... Apologies for that. So in the 6th HSR challenge, we had to manipulate unknown objects. We did that using a generic segmentation algorithm that we trained to just identify objects on this tabletop. HSR had no knowledge about these objects in advance. The test set was completely different than a training set, but would learn about these objects by inferring about their basic geometry from the segmentation itself and interacting with the objects to determine if they were deformable. And we also found we could similarly replicate this work using object detection. The benefit of this is the annotation is cheaper. And so here we're going to retrain our visual servo algorithm. We just need a single click of annotation to have a training object like the racquetball. And then after 13.3 seconds of the robot making different motions to learn how to relate actuators to those changes in the bounding box position, we were able to learn a control policy with the robot in 13.3 seconds. And then the robot could immediately track the ball using that learned control policy. And this was much smoother because the detection algorithm ran very fast, and we were able to make these control updates very fast on the robot. So in summary of the HSR challenges, we were able to perform manipulation on ordinary objects, which was the goal of the project. U of M was also the first team to use the hand camera or visual servo control, and released all source code before the 4th challenge. And then what we found is that by the 6th challenge, 80% of the teams were using visual servo control. So this was a paradigm shift in how these teams thought about how to do mobile manipulation with the HSR robot. And it also resulted in tech transfer to Toyota Advanced Research and Development. So that concludes this deep learning with classic visual servo control. Next, I'm going to talk about robot-supervised learning and domain adaptation. And part of the motivation for this work is TRI is basically doing work for Toyota, and Toyota is building this massive project called Woven City in Japan. And if you haven't heard about it, they want to get robots in the home. And part of the way that they're doing this is by building a massive amount of infrastructure and automation directly into the city itself. Well, we'd already shown that we know how to move these objects that are unstructured using HSR. But what we also wanted to show was that we could also have HSR learn from these interactions. And so if you want to think about this paradigm, you have a robot perception and control algorithm that's operating in some space, performing some tasks. But from those interactions with the environment, it's also able to collect data. Now, there's a learned object recognition system, whether it's detection or segmentation, working in the background. And so what we want to do is take some of that data, turning it into training data, and make updates to that vision algorithm so we can continue to perform tasks as things like domain shift happens or objects change. Now, I want to give some credit to another team from TRI that got past the problem of having annotation by doing sim to real. They did things like use 3D sensing and simulation and the real world to help bridge that gap. They also did domain randomization for the RGB image. But a fundamental limitation of this work is that if there were new objects that were in the environment, or there was something besides a tabletop that was being used, from talking to the researchers, this algorithm would break down. Now, on the other hand, the work that I showed for the HSR challenge, we were able to overcome this by taking data that the robot had collected and then taking that as training examples so we know we could operate well on these objects, whether it was detection, which takes about 7 seconds per bounding box, or segmentation, which takes about a minute per annotated example. But this still requires human annotation, and this is a fundamental limitation of this work. So the work I'm about to describe is what we call robot-supervised learning for object segmentation. And this is where the robot collects training examples from new objects that it hasn't seen before. But then the robot is actually going to annotate data itself so that that human annotation in the loop isn't necessary. So the basic paradigm is a robot's interacting with an object it hasn't seen before. It's going to automatically generate annotated segmentation masks that it can use to update its vision system. And so here you can see some examples of masks that we generated with the robot being able to collect multiple views of these in-hand objects and then later use that to update its segmentation system. And so the way that this works, broadly speaking, is with two algorithms. The first is a foreground background segmentation algorithm that would isolate both HSR's arms and the object in a segmentation mask, and then robot object segmentation that would enable us to isolate the object from that general segmentation mask that included the arm. So starting with the first component, the foreground background segmentation would use a depth image from HSR's RGB head camera, the RGB image, and a kinematic model of the robot. And so starting with the depth image, we'd have the object in hand, and we would project the kinematic model of where the robot expected its arm to be inside of that depth image. Now, if we then perform segmentation of the depth image, we could then look at the segments that both had a kinematic point associated with it and was in the range that we expected from the kinematic model and say, this is our foreground segmentation. Now, the depth image is inherently noisy and messy. And so what we would then do is take that mask, associate it in the RGB image, erode and dilate it to have different levels of confidence in what was the foreground object, and then perform grab cut segmentation to then have a clean annotation of the robot's arm and that object in the RGB frame. Now, the way that we did robot object segmentation is we used the foreground background segmentation approach to create a bunch of annotated training data for the robot's arm. We could then augment that with data from the COCO data set for different backgrounds, add foreground objects that included the arm. And in the end, what we had was a very reliable method for taking that initial foreground background segmentation, segmenting which part of it was the robot's arm, and then what we're left with is a clean annotation of the in-hand object, even if we've never seen that object before. So when we did testing with this, we could take a data set with 300 images of the robot's arm, expand that to a data set of 12,000 training examples for self-recognition. And in the end, we were able to beat out the previous state of the art in terms of annotation quality of these in-hand objects in both mean, intersect over union, precision, and recall sense. And more importantly, when we would take these annotations of the segmentation mask for these unseen objects, our ability to do object detection and segmentation for these objects improved. So the robot is actually generating its own annotated. And so instead of treating this as just a detection problem, if we have robot motion at the same time that we're detecting these objects, we can actually figure out what the depth of each object is using that robot motion. So to explain this, I'm going to describe our depth from motion and detection model. And this is where we have a pinhole camera model that's observing an object that we're able to perform detection on, but we don't know the depth. So from camera pose P1 and the projected image plane, we have a bounding box for the object, and that has some initial scale that we're going to call H1 associated with the height of the bounding box. Now, when the robot moves, we have a new camera pose P2, but also a new bounding box scale H2. But the robot knows what this relative change in camera motion is. And so when we account for that, we can actually solve for the depth in a metric sense using this equation right here. And understand this intuitively, if you're walking down the street and you look at an object that's close, it's going to expand much faster than an object that's much further away. And so we're basically leveraging optical expansion to determine what is the depth of the objects, given that the robot knows how much it moves while it's making these observations. In a similar sense, we don't have to use optical expansion. We can also use motion parallax using the bounding box offset. So here we have a camera position 1 and offset 1. The camera moves laterally, and we have an offset position 2. Using the known relative camera motion and lateral direction and the focal length of the camera, we can similarly solve for metric depth using the equation that you see here. Now, this is just a model. And if we have moving objects or bounding box errors or more complicated motions, the model is going to break down. And so this is why we introduced the object depth via motion and detection data set. And the data set essentially consists of n observations that we're going to feed into a network. Each observation is going to consist of a bounding box for an object in view and a camera motion as the robot is moving and continuing to make observations. After making n observations altogether, we'll predict depth for each object at that nth observation. And we started by doing this as an absolute depth loss, but we also came up with a dimensionless formulation where we normalized the inputs and then later multiplied the predicted relative depth by the known camera motion in a metric sense, either by the vehicle or the robot. And this would enable us to use the same network for many more applications and use cases. So just to show you what the training data looks like for this, essentially, we have a camera that we define, and we generate a bunch of 3D positions for an objects and bounding boxes that would be associated for that camera motion. And so it was very easy to make a bunch of training data. But we'd also add perturbations like bounding box noise, detections of the wrong object, and camera movement errors, so that when we went to apply this in the real world, the robot in this network had already seen these kinds of errors before. So then when it didn't necessarily know its change in pose perfectly or the bounding boxes weren't perfect, the network had already developed this ability to kind of infer from the observations overall, what is the accurate depth despite these errors? And so you can see this being used from a camera phone, a vehicle that's moving, and the original robot camera plus kinematic example. So we were able to do this for both detection and segmentation. Inference was extremely fast because these networks were not that complicated. They just worked on segmentation masks or bounding boxes. And they're also very low cost because we could generate the simulated training data basically for free. Now, the disadvantages were we would need a detection or segmentation mask for the objects that we were estimating depth for, and we didn't have any background information. So I'm going to kind of do a pivot here and go back to the initial thesis of this talk, was that vision with action in the sense of computer vision and robotics can change the world. And if you work at Box 51, you might be saying vision with action, you're just describing video. And to some extent, you're right. And I think underlying all these applications, you really have video is the primary data that's being operated on to infer these things about the robot's environment. And I want to give a really good example in my mind of how even untouched video has an inherent wellspring of structure, and self-supervised depth estimation is just one great example of this. So in case you're not familiar, self-supervised depth estimation is where we have a single RGB input to a network that's learned to predict a depth pixel given the RGB image for the depth for every single pixel in that RGB image. Now, what's not talked about as much is that usually this is in tandem with a pose estimation network that looks at a sequential input pair of consecutive frames in video and predicts an output pose in terms of translation and rotation. Now, why do we train this other pose network? Well, if we have one network that's predicting the depth and another network that's predicting the change in pose, we can actually combine these two things together and create a loss that can act as supervision just from video. So to do that, we have an RGB image, we have predicted depth. We use those two things together to create a 3D point cloud. Then we have the next frame in video. We predict what is the change in pose as we get to that next frame. And from that change in pose, we reproject that back into the camera frame if we move that predicted pose. Now, how do we have a loss for this? Well, we actually have that next frame in video. And so when we compare the reprojected image to the actual image, we have a signal that can be used as ground truth. And so these are how these two networks work together to train themselves using only video. So the nice thing about this is we get depth with RGB basically for free. We don't need these RGBD cameras anymore. We don't need any robot kinematic information. And this is all learned from clever use of structure in an untouched video. The primary limitation here is that there's no metric scale, but we're able to resolve this in our own test by adding weekly supervised pose estimation, either from a vehicle's velocity or from GPS if it was available on the data set. And with some work that we did with Ford, we're also able to augment this with semantic segmentation. And in this case, we would have from a single image, metric depth that we could do a full 3D reconstruction of. And then we could also do things like isolate the road in that 3D reconstruction just from a single image and do this in real time. Now, as I was saying, these video methods underpinned a lot of the robotics work. And we're able to take these methods that had been primarily developed on video from the Kitty dataset and other driving datasets and plug this directly into our HSR robot. And what we did is create an algorithm where the robot could create these simple motions and then learn to see in its environment in 3D. And so this is just another example of how these video methods can really plug in well to robotics and other applications, and also really complemented our previous work on object-based depth. So with that, that concludes the talk on learning robot perception and control using vision with action. I hope to in the future be doing more general foundational work, maybe just learning perception using video, so you could apply this to robotics or any application of your choice. I do want to give credit to everyone at Voxel 51. Having dug into the 51 platform, this was extremely easy given the tutorials that are available online, as well as the lectures people have given. I was able to take a lot of this robot data from years ago, quickly plug it into 51, and find these trends in the data directly that made intuitive sense to me as a roboticist. But the exciting thing here is anyone could look at this data, use these off-the-shelf methods, and be able to get insights whether or not they have that robot-specific knowledge. And I think this is going to create a good platform to really springboard from this, get to a higher level of abstraction, and work with a much larger scale of data and be able to do that in an intelligent way. With that said, I just want to thank mentors, including Jason Corso and other robotics mentors I've had in the past. Sponsors are the Toyota Research Institute and Ford, as well as numerous students that helped me with this work while I was at U of M. And with that, I'm happy to answer any questions that you might have.
And Brent, there are no shortage of questions. If you want to pop over into the Q&A widget, you got about a half dozen questions there if you want to tackle any of them.
Okay, I'll just start at the top. Can you comment on how robust the robot-supervised learning of segmentation masks are in practice? Perhaps at Agility. No, I cannot comment on them at Agility, but if we go back to those actual slides, and so you're looking at an MIOU of about 0.64, precision of 0.82, and recall of 0.71. And I think one way that this could be improved is by doing this in a more video sense. When we did this, we kind of did it with isolated images. So the next question here is, what's the difference between the way data is collected for ODMD versus structure from motion? So for the object depth from motion and detection data set, we did not have to collect any data from the real world. We basically knew from the pinhole camera model where objects relative to the camera would be projected as either a segmentation mask or a bounding box. And then we would create random motions of that camera within a profile that we defined in advance. And the network would learn directly from the bounding boxes. So then when we went to apply this to the real world, all we needed to do was couple it with another algorithm that would perform the detection or segmentation. And now we can estimate the depth without any human annotation having been provided. Good question. How does a learning depth / 3D reconstruction with a neural network compare to traditional ways like ColeMap? Well, actually, when we first started the project with Ford, we wanted to use ColeMap. And one issue with this was not only the runtime of ColeMap, which took a significant amount of time, and it became very clear that we were not going to be able to do this in real time on a vehicle. The other thing was when you ran it in a configuration that could run, let's say, even in a couple of seconds, the sparsity of the points were such that it really wasn't that meaningful. So I don't know if in theory, given enough compute and time, if ColeMap could be more accurate, but the runtime limitation just made it so there was no way we were going to be able to apply this to a vehicle. So to auto label objects, what label does it give? That's a good point. So we would have to basically let it know that this was this kind of object or this kind of object. But you could also potentially have this just exist in a latent space, because at the end of the day, when a network is performing classification, it's really just saying labels 0 through 20, 0 through 100, however many classes that you have. And then you just associate those labels after the fact with something that's meaningful to a person. So if you wanted to train directly on something that had semantic meaning, you would provide it to the robot. But if you think about something like a robot unboxing an order from Amazon, there would be a way to basically give that kind of information to the robot for free. It could potentially even use information available on the web associated with that object as a primer for training. So anyway, we provided the label, but there are ways that you could get around that maybe help with your question.